Hello and welcome to the first part of the demonstration for the plug gauge and round nuts project. This first demonstration, of course, is going to be making the plug gauge. Here's the print for the plug gauge itself. This is something that we went over during the lecture video. You'll notice that I covered up all of the information for the thread data because this is something that you are expected to find out on your own. But all of the information's been given to you by this thread specification, which you can cross-reference in the screw thread tables. This is a simple enough part, but it introduces a few new operations and another fixturing method that we're going to have opportunity to talk about here. Those are, of course, the knurling operation, the radius cutting operation, and we're going to be holding this knurled surface in a 5C collet, in a collet chuck. In order to keep with our plan to slowly hold your hand less and less as you progress through the course series in the machine technology department, we're going to give you this general procedure rather than a proper project planning worksheet, okay? But, I mean, going through this gives you pretty much all the information that you need, but you need to digest it and put it into the project planning worksheet format. So you are expected to have a project planning worksheet, all right, but you have to write it yourself. I'm also not going to be covering everything for this project in as much detail as I have for previous projects. I'll be focusing a lot of attention on new operations and new fixturing devices, new things that we haven't seen before. But things that you've already done before, I'm just going to sort of glance over. But I think that this demonstration will be a very helpful overview of the process to help you get a sort of visual, intuitive understanding of what we're trying to accomplish here. So I've already got the stock cut. This is our 1 3/4 inch, 1 3/4 inch mild steel. This is not the leaded steel stuff that we've used in the previous projects. Okay, this is just 1018 mild steel. That makes it a little bit more difficult to get good surface finishes on it because it's not quote-unquote free machining. It actually tears a little bit when you cut it. So without really nailing your speeds and feeds and having a nice sharp cutter and running it with flood coolant, it's kind of difficult to get good finishes. But there's no finish call out on this part, okay, so there's no issue there. I cut it off to 3 1/8 of an inch. The final part's going to be 3 inches long, so this just leaves me a little bit to clean up on both sides. So the first step is to put this in the 4-jaw chuck and indicate it. We're going to complete this part in 2 halves, okay? So first we're going to do this side that's got the necked down diameter that ends in a radius and has the knurls on it, and then we're going to flip it around and we're going to do the threads, okay? So we're going to be clamping onto the diameter over here that's going to end up being the threads first, and then we're going to cut this other stuff with the this part of the part exposed from the ends of the jaws. So that means that I have to have enough stick out so that I can finish all of these features without slamming into the chuck jaws. And so let's see, how much do we need? If this is 3 inches here overall, that's what it's going to end up being, and then this is 1 inch 500,000ths here for the length of the threaded section, then that means 3 inches minus 1 inch and 500 is going to be 1 inch and 500 for this side as well. So we need at least that much sticking out, and why don't we give ourselves just a little bit more than that? So let's give ourselves 1 5/8 or 1 3/4 of an inch. Okay, so 1 3/4 of an inch would be right around there. Clamp all this down now because we're really close. Remember that our tolerance here is basically 1/1000th of an inch. Okay, so we're good right there. So next step is to load our tool. This is that 80-degree diamond tungsten carbide insert tool, which has the negative geometry. This is what we've been using as a roughing tool, but we're going to use it both for roughing and finishing here. And let's go ahead and take a cut on that front face just to clean up the bandsaw cut. Okay, touch off right there, bring it back. I'm going to set up an indicator, okay, because we need to set a distance equal to 1¼ of an inch as soon as we're done taking this cut, so I might as well set it up now. Okay, I'm going to go ahead and take a cut of 20 thousandths across the face. Right there. Okay, and that looked like it cleaned up really nicely. Okay, so now I'm going to move back to where I just took my cut, okay, and I'm going to set the indicator to 1¼ of an inch. I'm going to use the 1 inch dimension on the 1, 2, 3 block to set this. So basically I'll put the 1, 2, 3 block between the carriage and the dial indicator, zero it, then I'll travel the carriage to that position and then go another 1/4 of an inch and set my zero there. So if I travel to where I just set my zero, that should be exactly 1 inch, and it is. Then go another 100, 250 thousandths right there. So that should be 1¼ inch, and it is. Good. I'm going to reset my indicator so that that's my new zero. Doesn't matter how you do it, but I like to give myself a couple of extra revolutions there on the indicator. Turn this on. I'm just going to touch off right there so I have a little witness mark. The reason why we're setting this at 1¼ inch rather than 1½ inch, which is what this length is going to end up being when all is said and done, is because we have to account for the material that we need to leave on here for the radius. The radius is 1/4 of an inch, which means that we need to leave 1/4 of an inch of material on here in order to clean that up fully and get a nice full radius. If we were to go 1½ inch with our cutting tool, then we would cut all the way up to a flat shoulder, leaving a small radius in the corner equal to whatever radius is on the cutting tool, which I think in this case is 1/32 of an inch. But if we go in afterwards with the radius cutting tool, there's no material left there to cut. If we were to cut this diameter with a tool that had 1/4 of an inch radius on it, then we could just cut up to 1½ inch. But that's not how we're going to do it. We're going to use a roughing tool to cut back a certain distance, and then we're going to blend that shoulder in to this diameter using the radius tool. And that's why we have to leave some material on here. Basically, we have to leave this much material on the length of the part, equal to the radius, 1/4 of an inch, in order to be able to cut that full radius and blend it from this outside diameter down to this diameter here. Hope that makes sense. Okay, touch the tool off like that. Set a zero. So this stock material is 1 3/4 of an inch in diameter, and I need to get it down to about 1 inch. Okay, so I'm going to take, let's say, 700 thousandths worth of cuts, and that leaves me 50 to finish. So the first cut's going to be 200 thousandths. Stop it right there and feed the rest of my way to the zero. Okay? Another 200 thousandths, we're at 400 thousandths now. Feed it the rest of the way. Another 200 thousandths gets us to 600. And then another 100 thousandths. Okay, let's take a measurement. That says 1 inch plus 25 and 20, so 1 inch and 45 thousandths. Now the final dimension here is going to be 1 inch, okay? But one thing that we have to remember is that the knurling operation is a forming process rather than a cutting process. So it scoops out the valleys and smushes up the peaks on the knurls, okay? So whatever diameter we start off with, the resulting diameter measured over the tops of the knurls is going to be higher, maybe 30 thousandths higher. So to stay inside of our tolerance for this diameter on the finished part, we actually have to undercut it to begin with. So I'll cut this down maybe 10 thousandths of an inch small. So that's 990 thousandths of an inch. So we're at 1 inch and 45 thousandths right now, minus 990. That gets us 55 thousandths. Now this is cutting so nicely, I think that I'm just going to leave the settings exactly the same and take a cut of 55. Stop it there, feed it to the 0, and then I'm going to feed out on the 0 like this, just so that I can clean up that shoulder. Perfect. So we're actually below the scale now of what we can read on the sleeve here. So we're actually at so 975 thousandths plus 16 and a half. So that's 991 and a half thousandths. So we're right inside of that 10 thousandths range that I wanted. Okay, time to remove this tool, and we're going to put in the radius cutting tool. Now, just a quick note about this. The insert is simply held with a tapered surface, okay? So the bottom of the insert has a little taper on it, and then the tool holder has a little taper in it as well, and they just mate together. So the downward force of the cutting action forces the two tapers together, and that's what retains this, okay? There's no clamp or anything like that, and you'll notice that really there's no specific indexing locations on this. You can index it anywhere in 360 degrees. So you just have to find good cutting edge somewhere in this range, right? Because that's where our cut's going to be happening. And you need to turn the insert so that you've got a good cutting edge right in that area. In order to pop this little insert out, you actually have to put a little punch on the back there. So you just punch out the back side of the insert, and that knocks the two tapers apart. Then you can index this and just kind of push it in there, and as soon as you start taking a cut, it'll seat itself. This is going to be a very broad forming cut, okay? So a lot of the cutting tool is going to be engaged in the workpiece at one time, so we're definitely going to have to struggle with chatter here, okay? So we'll have to mess around with the speed in order to get this to cut properly. But I have to say that it's not always obvious what exactly you're supposed to do. It makes sense to slow down the speed to get rid of chatter, but then sometimes that will cause the tool to get overloaded and it'll bite into the material and it'll be very difficult to get a good cut. So somewhat counterintuitively, it might make more sense to speed the RPM up, and then that will allow the tool to cut a little bit more freely, and that will result in a better finish, even though we're trying to mitigate chatter, if that makes any sense. So I'm going to try my luck with this first speed, relatively fast speed, and let's see what happens. Come over here to the shoulder and position the tool so that if I move to the left, the shoulder is going to touch on the apex of that round shape on the insert. Slowly move it in until I just touch off, right there. And I'm going to zero out my indicator. The next thing that I'm going to do is touch off on this diameter, okay? Because the way that I'm going to get a perfect blend from this radius into this diameter is by plunging in slightly on my last cut on the shoulder and then back feeding across the surface. So let me go ahead and touch off on this diameter and set a 0 right there. Okay, so now I'm going to make sure that my feed is set up so that when I engage the power feed, it feeds out away from the spindle. Okay, that looks good. Okay, so now I'm back to my 0 on the indicator, so where the insert is touching that shoulder, and I'm going to take a cut of 100 thousandths. feeding in by hand just until I get to my 0. And you can hear it shattering there. Right there. Okay, another 100 thousandths on the indicator. Feed in. So really dealing with chatter now. But it seems to quiet down as soon as you stop moving. It's like if you're feeding it fast, it doesn't chatter. If you feed it really slowly, it chatters, but then as soon as you stop, it seems like it cleans up. Okay, I'm going to take a cut of 40 thousandths now to leave 10 thousandths on the shoulder to clean up for my final pass. Okay, so I've moved to my final position, 250 thousandths from where I touched off on the shoulder. Feed in, nice and slow. Okay, almost there. So that's my 0. I'm going to go in another 3 thousandths or so, doesn't take much, and then feed out. There we go. So that radius looks okay. It tore this diameter a little bit, so the tool wasn't cutting very freely, but that's going to be okay. Okay, the next step is knurling. And there are 2 different styles of knurling tool. This first style here is called a knurl, and the nice thing about this is that it's very convenient. You've got one tool holder that has multiple different sizes of knurls on it, so it's got a fine knurl right there, a coarse knurl, and a medium knurl. Okay, you can see that the rollers, these knurling rollers, actually come in pairs. Okay, and all you have to do is index it to the one that you want, right? And then you actually push the tool into the part using the cross slide, okay? And then that's what gives you the pressure that's required to generate the knurls. The problem is that this generates a lot of side loading on the part, okay? So it's actually kind of difficult to get really high quality knurls in something like steel. There's a lot of deflection, and the knurls usually don't come out very uniform. This second type of knurling tool is called a clamp knurl, okay? Again, for obvious reasons, because it's got a pivot point and you clamp the 2 knurling rollers against one another. Okay? So the actual pressure that you need in order to generate the knurls comes from this screw right here. So you dog down this screw, and that forces the 2 knurling rollers together, okay? And then that's where you get your pressure. This usually generates much higher quality knurls, and professional knurling tools are based off of this design. Looking at the knurling rollers themselves, you'll see that they have these sort of triangular cutting grooves, or they're not really teeth, they're like forming teeth, and they have this sort of spiral or helical shape to them, and that the 2 rollers actually have opposite-handed helixes or spirals for their grooves, okay? So this one goes in this direction, this one goes in this direction, so that actually the 2 of them mesh together. And that's really important, okay? So when you buy these rollers and when you replace them, you got to make sure that you have opposite-handed rollers. Otherwise, you're not going to generate a diamond shape. You're going to generate basically one sort of diagonal cut rather than 2 crossing diagonal cuts, which makes the diamond. To replace these, you just knock out these 2 pins, take out the old rollers, put the new ones back in, and then knock the pins back in place. You should also lubricate these with something like Waze oil just to keep them nice and lubricated, because there's a lot of sliding friction. You really want to make sure that this is not gunked up with any like old chips or crusty oil or grease or anything like that. You want to make sure that it spins freely, okay? And you also want to make sure that the teeth on the rollers themselves are in good condition. They're not flattened, rolled over, they don't look worn, they're not chipped or anything like that. As an example of bad rollers, I've got these, which are, as you can see, loaded up with chips, and they've got big chunks missing from them. Okay, so that's definitely not good there. It's going to be very, very difficult to form good knurls with these rollers, okay? What's going to happen is it's just going to smush material around, and it's not going to create that nice clean diamond pattern, all right? The surfaces are going to be sort of rough, and the diamond's not going to be fully formed. All right, to actually install this in the machine, you're going to hold on to this little shank right here, and I would really recommend that you use one of these tool holders that has the flat bottom rather than the V-grooved bottom. And that's because as you're trying to adjust the position of the knurling tool, you may find yourself falling into that V-groove, which will get the whole tool kind of cocked out at an angle, and that's really something that you don't want to do. This way also you'll have more surface area in contact between the bottom of the tool holder and the bottom of the tool shank. So this is going to make for a more rigid setup. Now, one issue that you may be able to see already is that we are binding on the side of the tool here and the side of the tool holder. And so this is going to create some drag on the entire tool, which is something we don't really want. We want this to be able to move around, or rather pivot around freely so that it can find this diameter. So what we recommend people do is grab one of these aluminum shims. This one's actually 3/16 of an inch thick. And we're just going to put that in here on the tool holder in between the side of the tool shank and the inside of the tool holder. And you can see that that just kind of steps us out a little bit from the side of the tool holder and gives us that freedom of movement that we need. Okay, I'm just going to snug down one of these set screws because this knurling tool is going to have to be aligned to the part surface, just like a grooving tool or parting tool or what have you. And so in order to do that, it's really good to have one pivot point so that you have just a more controllable movement. So using my little white notepad as a sort of background to increase the contrast here, like I often do, I'm going to run this tool in really close and just make sure that it's lined up with the part so that the gap between the part and the tool is uniform from side to side. And that looks pretty good. Okay, I tightened down all of the screws, and it still looks pretty good, so I'm going to call that good. So in terms of the tool height, I'm just going to set it so that the center pivot right there is lined up with the center of the part, so the spindle axis. This doesn't have to be super precise, but it's good to set it pretty close. And so I'm just going to do this by eye, by sort of lining up the pivot with the center of the part. That looks pretty good right there, but let me bring it a little bit closer. So if you look at it from this vantage point, you can see that that hexagonal head on the pivot is lined up vertically with the 1-inch diameter that we cut on the workpiece. So that looks good to me. You can also see that shim in there nestled up against the inside surface of the tool holder between the shank on the knurling tool and the tool holder. Okay, the next step is to find the top dead center position of this diameter on the workpiece. That means that we need to push the tool in on the cross slide so that the knurling rollers are across the maximum distance of this cylindrical surface. The way to do that is actually pretty straightforward, okay? Let's loosen the clamping screw on the knurling tool and then just kind of push this in, okay, until it looks like we're on top dead center. Okay, so we're going to tighten the clamping nut just until the knurlers are both making contact on the two sides of the cylinder, okay, just very, very, very loosely, just so that they kind of retain their position, and so that as I feed them forward and backward, they both kind of grab at a certain spot, okay? The position sort of halfway in their movement as they're rolling is the position where they are top dead center on the two sides of the cylinder, okay? So like right there, they kind of grab and stop grabbing, and then they grab and stop grabbing. So in the middle of that movement, right there, that is our top dead center position. So I'm going to set that position as my 0 on the cross slide. I'm also going to clean up a spot right here on the side of the cross slide. And then I'm just going to create like a match mark. Okay, just take a Sharpie or something and then just draw from one side of the cross slide down to the mating surface on the carriage. Okay, and now I have a visual reference that I can use. The Sharpie marks don't actually need to be very precisely drawn, okay? Because even if they're some weird irregular shape, they'll still line up really, really well when you're right over top of them. All right, with the rollers over the top dead center position, we're going to bring the clamping nut down so that it's just hand tight. Okay, so that's hand tight right there. So I'm going to pull this back off of the part. And now I'm going to go 3.5 flats from this position. So not a full turn, 3.5 flats. So this is a hexagonal nut, right? So 3 flats worth would be a half a turn. So we're going to go just a little bit past a half a turn. So I'm going to use this edge right here as a sort of reference point. So if I were to turn it so that the flat lined up with the side of the tool, that would be a half of a flat. Okay, then that's 1 flat, 2 flat, 3 flats. So that was our 3.5 flats right there. By the way, I'm also going to take this opportunity to mark off my 1-inch distance for how long the knurled surface is going to be. Just doing that with a ruler. No need to get any fancier than that. Turn the spindle to a very slow speed and then complete that mark with the Sharpie. Yep, so right in the center of the Sharpie mark is 1 inch. Okay, we're ready to start this cut, okay? So we're going to go sort of 2/3 on, 1/3 off, okay? So not the entire length of the roller is going to start on the surface, okay? So that looks about right there. Because we're taking all of our depth in one cut, we're going to feed it relatively slow. So 5/1000ths of an inch per revolution. And I'm going to use a lot of tap magic. You really want to have a constant flood of cutting oil so that you can move chips and small debris out of the way so that they don't impact the surface quality of the finished knurls. Okay, so with the spindle still off, I'm going to go ahead and go back into my position. So judging based off of the Sharpie mark and off of the 0 on my cross slide. Okay, there we go. Now I'm going to turn it on and start dumping coolant on it immediately and start feeding it immediately. There we go. Lots of oil, folks, like a constant stream. Seems to be cutting okay. We'll find out in a moment. Okay, and right there. Go ahead and pull the tool back. Okay, and now we're going to clean this up with a wire brush. Let's take a look. Okay, so these knurls are actually looking pretty good. Right here in the center, they look almost fully formed, but you can see just the tiniest little bit of, it's like the peaks aren't perfectly formed. They're not perfectly sharp yet. All the way on the far left, you can actually see that the peaks are noticeably flat right there. So those are definitely not fully formed, and probably because I didn't linger in that area for very long. So it takes a few revolutions for the knurls to form. Over on the far right side, it looks like the knurls got folded over a little bit here on the corner where the material's a little bit weak. I'm going to put a chamfer on there, so all that's going to go away, but it's worth looking at. Okay, so I'm going to give this just a smidgen more of a turn just to get everything a little bit closer, all right? And then I'm going to go ahead and feed this back in. Going to be really, really, really careful to make sure that the knurls line up, okay? It's definitely possible to take another cut. You just have to make sure that the knurls line up. And I mean, they will. I mean, unless you really, really mush them in there without any regard for their alignment, I mean, they can't really help but line up. Okay, so I'm going to give it some more oil and going to take another cut. And let's take a look at that. Okay, so those are looking pretty good. They look fully formed from one side all the way to the other. They come to a sharp point. They're not like folded over, so the peaks are not folded over. If that were the case, then we would have overformed them. Okay, so as soon as they come to a sharp point, we're done. So these look great. Okay, I'm going to remove the knurling tool now. Okay, so now it's time to put that 30 thousandths by 45 degree chamfer right on the end. We do that to clean up the end of the knurled surface because it's actually folded over quite a burr just by smushing that knurled material around, okay? And so we put that little chamfer on there just to give it kind of like a nice smooth entry to the knurled surface. And we're just going to use the 45 degree chamfer tool to do this. So set the correct speed and then turn it on. Okay, we're just going to sort of bump up on the edge of the part, put an indicator on the way surface, zero it, turn the spindle back on, and then we're going to feed the carriage to the left 30 thousandths of an inch. And there we go. You can see that that really completes the whole look of the knurls. Okay, so this part is ready to come out. So there you have it, folks, and it came out pretty nicely. You'll notice that there's some debris, some chips adhering to the knurled surfaces in there. It can be really difficult to clean out these knurls, so a wire brush usually does the trick, but you can also take it to the wire wheel and just knock all those chips out of there. Try to follow the actual grooves of the knurl, so that angled groove, in order to get the best result here, so that you don't flatten the knurls and so that you actually remove the debris. So now we have to talk about what we're going to do to machine the other side. Okay, we're not going to use the 4-jaw chuck because the 4-jaw chuck would squash the knurls. Okay, so we have to protect the knurls. We also want to reference off of that knurled surface so that it's relatively concentric to the spindle axis, so that when we turn the other features on here, they're also relatively concentric to that surface. And a good way to do this is to use a collet chuck. Okay, this is a 5C collet, and it fits inside of a 5C collet chuck, which I'll show you in just a moment. The way that these collets work is just like the R8 collets that we're used to using in the Bridgeport, okay? They just have a different taper on them, called a 5C taper. And instead of having a drawbar thread in the middle, they have threads on the outside, and that's what actually draws the taper up into the collet chuck. Because the collet is split in 3 places along its axis here, when it gets drawn into the taper, it collapses the inside diameter. Okay? That inside diameter is very, very concentric to the outside diameter here and to the taper. And it's also made to a very, very accurate diameter. Okay? And those diameters come in increments of 1/64 of an inch. So you can see we have a 1 inch here, 1 1/64, and 1 1/32, and it goes on and on and on. The trick here is to find the size that is closest to the diameter that we're trying to hold. Now, your diameter is never going to be exactly the same size, right? And so is it better to be a little bit bigger or a little bit smaller? The thing to remember here is that the collet is a flexure, and it's held stationary back here, right? That's where the split stops. And when you tighten this down in the chuck, it's the end here, the end of the collet, that actually comes down around the workpiece material. So if you try to put a piece of material in there that is significantly smaller in diameter than the bore of the collet, then the collet's just going to pinch right on the end, right? It's going to come and pinch down on the outside of the material, but it's not going to be holding back here at all. Likewise, if the material is significantly larger than the diameter, okay, then it's going to be pinching back here, and up here we're not going to get anything. So which one of those is worse? Well, it turns out that holding onto a piece of material that's too big is the worst case scenario, okay? Because then we're going to be holding back here and not here, and so where the part is actually secured is going to be much farther away from where the cut happens. The other thing that's going to happen is that it's going to spring the collet open, okay, which can permanently change the size or the position of those three little fingers in there. So that's something we don't really want either. So if anything, we would prefer for the workpiece material to be just slightly smaller than the collet diameter, but not much. Only about 2/1000ths of an inch is our max. But neither of these cases is desirable, okay? Because in either case, you're pinching either here or back here, and so you're not holding onto a very long section of the diameter. Basically, you just create like a pivot point, either back here or up here, and as soon as you start putting any kind of force on the part, it's going to knock out of alignment. So it's really, really important that we get as close of a diameter as possible into the collet. So we really should check what the diameter of our part is right now, the diameter that we want to hold on to. So let's see what the knurl came out to. Okay, the knurl came out to, that says 1 inch, 12.5 thousandths is what that says to me. Okay, and we've still got a little bit of original unknurled surface here, so let's check what that is. Okay. That came out to 975 plus 12, so 987.5. So we're at 1 inch, 12.5 right now, after the knurl, and before the knurl we were at, let's see, 987.5. So the surface got smushed up 25/1000ths of an inch. That's pretty interesting, but it's not what we're looking for. What we're looking for is, based off of the surface we're trying to hold, what is the next largest nominal size collet that we can use to hold it? So 1 64th of an inch is 1.015625, okay? That's just a little bit bigger than our diameter that we cut on our part, okay? So let's see how much bigger. Okay, 3/1000ths and 1/10 of a thousandths. This is almost close enough, okay, but it's not quite there. So how do we make up that difference? You guessed it, shims. In this bag o' shims, we have some relatively wide shims cut from sheet of various different standard thicknesses, okay? Going 4/1000ths, 6/1000ths, 3, 5, 1, 2. Okay, so going all the way up to 6/1000ths and all the way down to 1/1000ths. So I'm going to use a 1/1000th shim, okay, because if I wrap a 1/1000th shim around this diameter, that's going to build it up 1/1000th of an inch per side, giving me 2/1000ths of an inch total. So I'm going to go from 1 inch and 12.5 thousandths to 1 inch and 14.5 thousandths. And that's going to be enough to be within that 2/1000ths window of my nominal collet size. Your part is likely going to need a different size shim because your part's going to come out to a slightly different size, right? So just pick whichever one gets you closest, okay? And remember that when you're building up the diameter, you're going to get double the shim thickness, because this amount is going to be added radially, right, on both sides of the diameter. Okay, so just wrap it around like that, and then that whole thing goes into the 1 16th inch diameter collet like that. Now remember that this surface right here is significantly lower than the knurled surface, okay? So we only are going to be clamping on the knurled surface. So there's no need to push the part in any further than the end of the knurled surface. And you especially don't want to push it in so far that you're actually touching the corner radius that we put in there, okay? Because that's going to do two things. One, we're going to be clamping on the tip of that radius instead of clamping on the knurled surface, and so that's not going to hold this very securely at all. And the other thing is that it's going to put a ring of deformation right at the point where the collet is actually squeezing on the radius. Okay, it'll be really noticeable. So just back here is really all we need. Okay, so when you're installing this, again, just make sure that everything is really nice and clean, okay? And there is a little keyway right there, and that really needs to line up with the key that's in here. Okay, it's really far back there, but it's got to line up. It's not even really going to go in until it lines up. There we go. And then all you have to do is rotate this outside handle here, and that'll draw it in. It takes a minute. Okay. You can put it into low gear or step on the brake in order to get it the rest of the way, and it should be pretty tight. So just like that, okay? The nice thing about collets is that as long as they're maintained and you're using them appropriately, they can hold parts very concentrically to the spindle axis. And they make these in various different sizes, bigger and smaller than the 5C. They make them in various different designs. Some have more splits or splits going multiple different ways in order to increase the surface area of contact. But these 5C collets are very common. And so now we don't need to indicate this at all, right? All we need to do is go ahead and face the end of the part, turn the diameter, put some chamfers on there, and then turn a thread. Now, one thing I want to say about turning these threads is that this is still not a very securely held part, okay? Not nearly as securely held as if you were to put it into a 4-jaw chuck, okay? So all of those depths of cut that you're taking on the compound, you're going to want to have those. So if the chart in the operations manual tells you to take a cut of 20 thousandths or something like that on the compound when it's set at 29 degrees, you're actually going to take 2 cuts of 10. So you're going to take twice as many cuts with each one being a half of the value. Hope that makes sense. That's just going to make sure that you don't hang up on the cut and then the part will spin inside of the collet and then you'll lose the position for your threads. By the way, if you look at the chart for depths of cut for threading in the operations manual, you'll see that there are rows for 11 TPI threads and 13 TPI threads, but there's no row for 12 TPI threads. I'm not 100% sure why this is, but it's probably because 12 TPI threads are actually not that common. So there are no coarse pitch threads that have a 12 TPI. The only time you get a 12 TPI thread is when you get to the larger major diameters, and then they become the fine pitch for those larger diameters. That's the case with our 1.5 12 UNF3A threads. The point is that we won't be able to follow any of these rows outright without any kind of modification. If you look at the 13 TPI row, it says that the ultimate depth setting for 29 degrees, meaning how far you're going to travel on the compound, is 54 thousandths of an inch. And for 11 TPI, it's 64 thousandths of an inch. For 12 TPI, it's going to end up being something more like 58 thousandths. So what I would recommend is that we start with the first cut in the 11 TPI row, so that's a cut of 15 thousandths, and then we start following the 13 thousandths TPI row. That should make up for that missing 4 thousandths of an inch. But also keep in mind what I just mentioned, which is that we're going to be cutting each one of these numbers in half and taking each depth of cut in 2 passes. Another thing is that after you've turned down the major diameter of the threads, that's the point of no return. Once you've turned down the major diameter of the threads, you have got to go in and actually cut those threads. Because, you know, we've got a shim in between a knurled surface inside of a collet. This thing is going to repeat reasonably well, but again, not perfectly, okay? And so you really need to take a skim cut on the major diameter at the very least if you're going to take it out and put it back in. So at the end of the day, if you're not going to be able to get to threading, maybe just leave yourself like 30 thousandths or something on the outside diameter here, and then come and take a skim cut on it just to clean it up to the major diameter, and then go in and thread. Anyway, folks, I'm going to leave you to it. All right? I think that you know enough at this point to be able to finish the rest of this part. I mean, it's all stuff that we've done before, and I think that it's a really good challenge to try and figure out how to do it on your own. But I will leave you with this little fast-forward teaser showing you the general process. All right, folks, there you have it. I'll see you in part 2 of this demonstration, in which we make a round cap nut with an internal blind threaded hole. See ya.